When we were first learning about light, we learnt about the amplitude and the wavelength of a light wave. So let's go back and look at a light wave again to remind us. So remember that light is a transverse wave because it goes up and down as it moves through the air or through a material. And remember that the amplitude is how tall the wave is. And the amplitude makes the light brighter or dimmer. So amplitude affects the brightness. And we also learnt that the wavelength is the distance between the two troughs or the two peaks. It's the same distance. So the wavelength is here. And we learnt that the wavelength changes the color of the light. So the important thing to remember is that different wavelengths of light have different colors. Different wavelengths have different colors. And what scientists have discovered is that the red colors, the reds and oranges, have longer wavelengths. Longer wavelengths compared to the blues and the violets, and these have shorter wavelengths. So here are all the colors of the rainbow, and this is all the different colors that we can see as humans. And if there's a color that's not in this rainbow, then it's a combination of some of these colors that we can see. So there's a good little acronym to remember the rainbow. It's ROYGB, Roy G. Biv. And we can see that stands for red, orange, yellow, green is in the middle, blue, indigo, which is dark blue, and violet, which is the purple color. So all the colors of the rainbow together, this makes up white light. Light that comes from the sun or from a light bulb. So actually, white light contains all the colors of the rainbow. And let's look at some different colors of light and picture the wavelengths. So we saw up here that red has the longest wavelength out of all the colors. So if we are looking at a red ray of light, if we could zoom in and actually have a look at it, it would have long wavelengths like this. That's red light. And green light in the middle, that has an average wavelength, so a little bit shorter. So green's in the middle, and then dark blue or violet, that has an even shorter wavelength again. So a blue or a violet light looks like that. But remember, the amplitude or the height of the wave also tells us how bright or dim the light is. So down at our examples, we can have blue light that's dim. So it has the same wavelength, but it's not as tall. So it's still blue light, but it's dim. The last thing to look at now is how do actually different things have a different color when we look at them. And the reason for that is that different colors get reflected and absorbed differently. So let's look at a piece of paper on the table firstly. So when we look at a piece of paper, there's light that's come from the sun, and that contains all the colors of the rainbow because it's white light. So white light is coming from the sun and it's hitting the paper. It's got a red ray of light and green rays and blue rays and all the other colors. And white objects, they reflect all colors of light. And they don't absorb any colors. So paper, all colors are reflected. Which means they all bounce off the surface, the red, the green, and the blue. So when they hit our eye, here's our eye looking at the paper. When they hit our eye, all the colors of the rainbow are still there. So to us, that piece of paper looks white. But let's look at something else that actually has a color. Like if we're looking at some grass outside. So obviously grass looks green to us. And the way that it appears green is that, again, all the colors of the rainbow come down from the sun or from a light bulb, whatever's lighting up the grass. But grass, because of the chemicals inside the actual blades of grass, it absorbs all the reds and the blues. Just those wavelengths. So red and blue colors are absorbed. And only the green light is left to be reflected. So only the green manages to reflect off. And that means when we're looking at the grass, we're only picking up that green light. So the grass appears green to us. And this is what happens with every colored object. Different materials absorbed different colors of light, and they reflect what's left over. So really, what we're seeing as color is what's not absorbed by that object.